All right, today we're putting on our detective hats and diving deep into the world of linear algebra. Our mission? To solve a classic whodunit from a university exam. We've got three suspects, three sets of vectors, but we need to figure out which one, if any, is a true vector subspace. So let's get this investigation started.
So here it is, our central mystery. We're given these three options, and we have to figure out which one fits the definition of a subspace. Now, this isn't just about memorizing some rules. It's about actually applying a really rigorous test. So what are the rules to get into this exclusive mathematical club anyway?
First, let's lay down the law. A vector subspace isn't just any old collection of vectors. You got to think of it like an exclusive club inside a bigger space, say like R cubed. And to get in, every single member has to follow three very specific, non-negotiable rules. And here they are, our three-point check. These are the golden rules. Every suspect has to pass all three of these tests. If it fails even one, well, the case is closed. It absolutely must contain the origin, it must be closed under addition, and it has to be closed under scalar multiplication. Let's bring in our first suspect for questioning. First up is case file A, this sign set. It's a collection of vectors in R3 that are defined by the sign function. So for any real number x you plug in, you get a vector that looks like x, sine x, 0. If you picture it, it kind of creates this cool-looking wave in the xy plane. It looks interesting, for sure, but does it follow the rules? Let's run the tests. You know, what's really fascinating here is just how quickly this whole case falls apart. So, test number 1. Does it contain the 0 vector? Yep. If you plug in x equals 0, you get 0, sine of 0, 0, which is just 0, 0, 0. Easy pass. So far, so good. But test 2, closure under addition, this is where it fails, and it fails spectacularly. See, if we add two vectors from this set, their sum has to have that same form. Some number, sine of that number, 0. But we all know from basic trigonometry that sine of x1 plus sine of x2 is just not the same thing as sine of x1 plus x2. That is a clear violation. Case closed. This is not a subspace. All right, moving on. Next up, we have case file B. Now this set is defined by two fixed vectors, u1 and u2, and a single scaling factor, gamma. What this really means is we have two lines, and both of them pass right through the origin. One line is just all the multiples of u1, and the other line is all the multiples of u2. This one seems like it might have some potential. Okay, let's run the tests. Does it pass the 0 vector test? Sure does. If you just set gamma to 0, you get the origin. No problem there. But again, it fails on addition. Here's why. If you take a vector from that first line, the u1 line, and you add it to a vector from the second line, the u2 line, the result is some new vector that, guess what, isn't on either of those original lines. The set includes the two lines, yeah, but it doesn't include the entire plane they might span, so it's not closed under addition. Another case closed. Okay, time for our final suspect. And I'll admit, this one is the most abstract of the bunch. We're not in R cubed anymore. We're in the space of 3x4 matrices with complex numbers as entries. Our suspect is the set of all of these matrices, but only the ones whose rank is less than or equal to 2. Now, the rank of a matrix, to put it simply, is basically the number of linearly independent rows or columns it has. So this is a club for low-rank matrices. Let's see if it qualifies.
Let's run the diagnostics. Does it have the 0 matrix? Well, the 0 matrix has a rank of 0, which is less than 2, so check. It passes the first test. But what about addition? Here's the trap. Just imagine you have two simple matrices, both with a rank of 2. But if you add them together, you can actually end up with a matrix that has 3 linearly independent rows, making its rank 3. Because the rank isn't guaranteed to stay low after you add them, the set is not closed under addition, and that means it is not a subspace. So, after interrogating all three of our suspects, we found that not a single one of them holds up under scrutiny. Every single one failed a critical test, and that leads us to the only possible conclusion left on the table, which is option D. None of the answers are correct. Our investigation has revealed 3 imposters.
So let's just do a quick recap of the case file. The sign set, it failed because sign just isn't a linear operator. It breaks the addition rule. The scaled pair failed because it only contained 2 lines, not all the possible combinations between them. And the low-rank matrices failed because rank is a property that isn't always preserved when you add matrices together. Each one had a single, fatal flaw. And this, right here, is probably the most important lesson from our whole investigation. In math, especially in linear algebra, the rules were absolutely absolute. To prove that something is a subspace, you have to show that the rules hold for every single element, no exceptions. But to prove that it's not a subspace, all you need is a single counterexample. One instance where the rules break is enough to completely disqualify the entire.
So, we solved the case, all by applying a rigorous three-point check, and now you have the tools to be a subspace detective too. The real question is, what other sets out there can you put to the test? Can you spot the real subspaces from the imposters? Thanks for joining this investigation.